Good morning, students. So today in our class we will discuss the volume integral, and then we learn about few theorems like divergence theorem and Green theorem and Stokes theorem, and how to use them to solve different applications. So first of all, we'll start the discussion with volume integration, and the volume integration, as we have already done the line integration and the surface integral. I hope you will be able to understand what it is, and accordingly you can understand, I hope, the volume integral part. As you know that we are doing the line integral, surface integral, and volume, and along with those theorems we have to learn. Myself, Dr. Pradeep Sharma from University of Engineering and Management, and we'll try to learn today the part which is of our syllabus, the volume integral. Like we see that here in this section, we consider integral of scalar or vector fields over volume defined in different, you can say, curvilinear coordinates, Cartesian or so. So in Cartesian coordinates, we can say the small volume dV can be given by dx, dy, and dz. Okay, so we can redefine this for cylindrical or spherical also. Cylindrical dV is equal to r dr d theta dz, and for spherical dV is r square sine theta dr d theta d phi. So we can have the three type of you can say the small volume element, because as we have done like in surface integration, the complete surface is defined by the collection of small surfaces. As we are doing the same part here, the volume can be considered, the entire volume can be considered as the collection of small volume elements. So these volume elements in Cartesian, cylindrical, and spherical can easily be defined. And we have done already in the scalar and vector part, where we have defined all these things, the coordinate systems. So if we devise, you can say a new coordinate, UVW. So dV, the small length element in those coordinates, is the Jacobian of that those parameters, Jacobian of that function. So given a vector field F, F1 I cap, F2 G, and F3 K, so we can define F dV over that volume is F1 dV for I cap, F2 dV, J cap, and F3 dV. So usually the integral of a volume integral is a scalar. So you know that the volume is a scalar quantity, so whatsoever the value will be coming from this integral, that will be the scalar value. And because the volume comprises of three parameters, three at least parameters, the length, breadth, and you can say the height. So three parameters we can easily calculate. It will be triple integration, and here x, y, z are the parameters. Here r theta z is the parameter. Here r theta phi is the parameter. So accordingly, we will be having the three integral values to find the volume integral. Now to move ahead, we have to see the integral theorems. First, we are trying to see what basically these integral theorems comprise of. So we have seen that there are line integrals, surface integral, and volume integrals, but there exists a relation between these kinds of integrals. In certain circumstances, we have to correlate in some conditions or some environments a line integral with a volume integral, or a volume integral with a surface integral, or a surface integral with a line integral, and vice versa. So these relations are generally gathered under the label integral theorems. And these theorems link the concept of line and surface integral through the differential operator del. So we can see that del operator is basically playing an important role while defining the integral theorems. So first of all, we are trying to define the divergence theorem. So a statement of the divergence theorem, as you are seeing over here, it is understood that first of all we need to understand the divergence theorem. It is the relation between the volume integral to the surface integral and the flux of a vector field, because the surface integral, if this f dot n ds or f dot ds over that surface gives the flux of that f field across that surface. So flux of a vector field f across a closed oriented surface in the direction of the surface outward, unit normal vector field n equals the integral of del dot f. It means it is the divergence of that field over that region enclosed by the surface. So over that region means is the volume integral del dot f. It means we can easily say that the volume integral of any the surface integral of any vector field here will be equal to the volume integral of divergence of that vector field. So there is a relation between the surface to the volume integral. And already we have seen that this surface integral defines the flux, which is given by f dot n ds. So in the direction of the surface outward unit normal vector field. So this theorem relates the surface integral of a vector field with the volume integral of a scalar field constructed as the divergence of the vector field del dot f, and the surface S over which the integration is performed is indeed the boundary of the volume V. So intuitively it states that the sum of all sources minus the sum of all sinks gives the net flow out of the region, because the divergence is actually all that above. So we can easily see over here that this theorem also requires some mathematical conditions. The volume V must be compact and its boundary surface must be piecewise smooth, and the vector field F must be continuously differentiable on the neighborhood of V. So this theorem is also called Gauss theorem or Ostrogradski theorem, and is a special case of the more general Stokes theorem that we will see in the next session where we are going to see. So this theorem is very important in physics, where we are using this in electromagnetism or in fluid dynamics, where we need to find the divergence. So divergence basically over here we can easily find using the flux and the flow whatsoever. So it's very important, and I request all the students to see over here, wherever you see the Gauss theorem, Gauss divergence theorem, or simply divergence theorem, or Ostrogradski theorem, so you can easily make out that there is a relation between a surface and a volume integral. Okay, and how you will define it? In a very simple manner, you can say that if there is a vector field, the flux of that vector field over that closed surface will be equal to the volume integral of the divergence of that vector field. Right? So it will be in a very simple way you can conceptualize. So corollary to this vector form of divergence theorem is integral u ds. So it will be del u dv. So where u is a scalar field and both sides of the above equations are vectors. Okay. And this theorem is stated in R cube. It has two other versions in lower dimensions also. So the one dimension version R is reduces to the fundamental theorem of calculus that links the concept of derivatives and integral of a scalar field. So we can easily point out here fx is equal to a to x ft and dt and f to x fx. And R square, which is the two-dimensional version, is called the Green's theorem that links the line integral of a vector field over a curve with the surface integral over plane. So we have to see in the next section that R cube is the divergence theorem and R1 is the fundamental theorem of calculus. R2 is the Green's theorem. So that we have to understand. Now what is Green's theorem actually? The Green's theorem says that if it's a closed curve, so C is a closed simple curve in xy plane, traversed counterclockwise, and M and N are suitably differentiable functions of x and y, then we can write closed curve C m dx plus m dy, double integration over r del n by del x minus del n by del y dx dy, where this area integral is over the region R enclosed by the curve C. So Green theorem is also the special case of Stokes theorem. So you can see that divergence theorem as well as the Green's theorem can be the special case of Stokes theorem, and we can easily find out. Now the corollary to this Green's theorem, we can easily find that the area A inside A is a closed curve C bounding a region B in a plane, like in this diagram. And MA is half of this R plus dr. You can easily find out this. The half is the closed curve C x dy minus y dx dot k from here, A to B. Okay, so C1, C2, C3, C4. Accordingly, and if we are given a curve in parametric form, xy is equal to ft, gt, so we can easily find A in terms of k. And now we can see the Stokes theorem. The Stokes theorem says that if F is a suitably differentiable vector field and C is a closed path bounding an oriented surface S, so we can say that the line integral of that vector field will be equal to the curl, you can say the surface integral of the curl of that vector field. Okay, so again I am saying that the line integral of the vector field around that closed curve, closed path C will be equal to the surface integral over that closed surface S of the curl of that vector field, and that is equal to this integral S del cross F dot n ds. So where C is traveled counterclockwise with respect to this unit vector, unit normal n of S. So counterclockwise as seen from the positive hand side of S. So this theorem relates the line integral of a vector field with the surface integral. Okay, and the surface integral to the volume integral is our Gauss divergence theorem. Okay, so constructed at the curl of the former del cross F. Now, according to vector form of this Stokes theorem, we can say that it can be written as UA dr del cross UA dot ds, and we can find if we can choose A is equal to ijk. So we derive the vector equation integral u dr for this curve is equal to ds cross del u for this surface. So this is the Stokes theorem. And important applications of divergence, Green and Stokes theorem you can see over here in electromagnetism for Maxwell laws. We see over here that in Maxwell laws, in the differential form, del cross E is equal to minus del B by del T. And for integral form, we have defined this. So by, you can say, deriving these equations for differential integral form, we are using the divergence, Green's and Stokes theorem. The Faraday law of induction as well as Ampere's law with Maxwell's extension, del cross H is equal to J plus del T by del T, and in integral form also. So we are using these divergence, Green and Stokes theorem. So summarizing all the above in general theorem, it's not, you can say, in general, we cannot examine, it's not examinable. The integral of a differential form, omega, over the boundary of some orientable manifold omega is equal to the integral of its exterior derivative, dw, over the whole of omega. So again I am saying, the integral of a differential form w over the boundary of some orientable manifold omega is equal to the integral of its exterior derivative dw over the whole of omega. So we can write this like this: integral w over the entire omega will be equal to the integral of d omega for the entire omega. Now, fundamental theorem of calculus says that fx dx is the exterior derivative of the zero form, that is the function f, in other words, that df is equal to f dx. And a closed interval AB is a simple example for one-dimensional manifold with boundaries. And divergence theorem, Green's theorem, Stokes theorem is a special case of this general Stokes theorem with n is equal to 2. And once we identify a vector field with a one form using the metric on Euclidean 3 space. Now we are going to discuss the conservative fields and the scalar potentials based on this discussion what we had. So we have studied the generalities of integral theorems. Now we will analyze some concrete situations of special interest. We can say that a vector field f is said to be a conservative field if the value of the line integral p to q f dot dr between endpoints p and q depends only on the endpoints p and q and not on the path taken between. So it's a conservative field condition that it should not be depending on the path, it should be independent. So for a conservative vector field, the integral f dot dr around any closed path must be zero. And a vector field is conservative if it is irrotational or curl free. So del cross f is equal to 0, so the curl is 0, so it is irrotational, the f is irrotational. And it shows that a scalar field phi r such that f is equal to del phi is scalar potential for f. It is the value for the scalar potential for that vector field. And a scalar field is conservative if it has a scalar potential. So a vector field is conservative if it has a scalar potential. If f is conservative, so r1 to r2 f dot dr will be phi r2 minus phi r. So these are the conservative fields conditions. I hope many of you have already know these facts. So conservative field and scalar potentials already the physical interpretation is very simple to understand. But we are trying to see the most the important parts, that the gravitational field is an example of a conservative field force. Its associative scalar potential phi r is a scalar field for the potential energy. And without loss of generality, a minus sign is introduced, f is equal to minus del phi, where phi r is equal to minus a to r f dot dr. To emphasize that if a particle is moving in the direction of the gravitational field, the particle decreases its potential energy. And energy conservation in terms of over here, if you see B to A and then again A to B, the kinetic energy and then the potential energy, and potential energy turns to kinetic energy. So energy we need to use to take a bike from B to A is stored at potential energy, and the same is released in terms of kinetic energy as we drop it from A to B. So this energy is independent of the slope, that is path independent. So divergence free fields and potential vectors, if we say a vector field f is divergence free if del dot f is 0. And as the divergence describes the presence of sources and the sinks, a divergence free field means that the balance of sources and sink is nil. So that is most important part as far as the divergence free fields are there. So for example, the magnetic field B is empirically divergence free. Why? Because whatsoever the field of lines moving in one direction will be equal to the moving of the number of field lines coming in that direction. So that suggests that del dot B is 0 actually. The divergence of magnetic field is 0. And it also suggests that magnetic monopoles do not exist. Magnetic monopoles, you can say isolated magnetic charges, do not exist. However, string theories do predict their existence. So it's concurrently, you can say, a point of discussion right now. But electric monopoles charges, plus charges there, so it can reside anywhere. The plus charge can be there with the outward flow of field lines, as the minus charge can be stable everywhere with electric field lines going into this. Okay, but magnetic monopoles, north and south, they cannot exist and independently. Now divergence free fields in potential vectors del dot f is equal to 0. If it is there, then there exists a vector A such that f is equal to del cross A. In that case, A is called the vector potential. So vector for the vector potential, the condition is that there exists a vector A such that the divergence of the field is 0, first condition, and f is equal to then del cross A. In that case, we say that A is a vector potential. Gauge transformation, in some problems we used to have that one can always add an arbitrary function of the form del phi to A and get another perfectly good vector potential for f. So del cross del phi is 0 for any phi. So you can see over here the resultant is f. So most of fundamental physical theorem are Gauge invariant. So thank you for this. For numericals, we'll touch upon in the next classes. So we'll discuss the numericals on line integrals, surface integrals, volume integrals, as well as the value for the numeric theorems, divergence theorem, Green's theorem, Stokes theorem. So we'll try to have the numericals, at least 2 to 3 numericals for each. And if you feel any doubt or any problem using these concepts, kindly let me know accordingly. Okay, thank you.